Hello, everyone. My name is Judit Szulagyi. I'm from Switzerland. I have an ETHZ-funded research group. We are working on disks, mainly in the planet formation context. But I'm going to give this talk that way that I compare it with the disks that we talked about during this conference, the mini disks, for example, around black holes. So this is how simulation look like for us. This is giant planet which forming here around the solar mass star. This equivalent of 3 times 10 to the minus 3 Q. And these giant planets, these are opening gaps, of course, and this is what you see with blue. And as we zoom closer, we see the planet vicinity. We can resolve the planet because we have static mesh refinement. And then there is this circumplanetary disk, which is the equivalent of the black hole mini disks. For us, this is the place where the moon's going to assemble later on. We have also radiation transport in this code and in this simulation, so that means that we also calculate the temperatures. So this is our code. It's a good enough code, mesh refinement. It has various types of coordinate system, including rotating coordinate systems. It's fully multi-fluid now, so we can handle also dust and various grain sizes. And it has flux-limited diffusion approximation for the radiative transfer with 2-temperature approach. And currently, my postdocs and students are working on to add self-gravity, non-ideal gas equation of state and particle tracers as well. So this is how the dust included simulation look like. So this is multi-fluid, orange is dust, blue is the gas, and here is where the planet is forming. So in this case, when we have both dust and gas, we consistently calculate the opacity from the local dust and gas densities. And one of the things that we have found that if the planet mass is quite massive, then the spiral wicks of the planet going to stir up the dust inside these disks. So it's no longer settled. I don't know whether this is important for AGN disks or not, but maybe. So the simulations are quite similar for the black hole and the planet case. We find also mini disks. We call them circumplanetary disks. I found only 2D mini disk, but I don't know exactly every single paper in the field, in your field, but this is how the circumplanetary disks look like. They look very much the same. The difference between our two communities is that we have very different opacity and temperature regimes. For the planetary case, we are talking about temperatures between roughly 30K to very maximum 10,000 Kelvin. This is just 3 opacity table what people use. I use actually a 4th one, and Jawan uses a 5th one. Here below 1500K, we have dust, and that's the main source of opacity for us. What is the composition of this dust, how much silicates and carbon and water ice we have. This is kind of something we disagree on among the different people in the field. But the gas opacities we do agree on. It's hydrogen, helium, solar composition. Now, I took out from young phase papers what opacities you guys are using in the black hole disks. So here it seems that the temperature is well above our case, more than 10,000 Kelvin. It looks to me also more optically thick because these are going up to 10 to the 4 centimeters square per gram. And yeah, it also looks to me that the larger is the temperature, the smaller is the opacity for you. For us, it's the opposite in most of the regimes. So what does this mean? Planetary disks have very low ionization or almost no ionization. That's the reason why those colleagues who are doing MHD simulations, they use only non-ideal MHD. We don't have MRI. We cannot sustain MRI in the protoplanetary disk nor in the circumplanetary disk. We don't use, most of us don't use alpha viscosity. Therefore, I personally use kinematic viscosity because that's either way you're going to have. Now, the question is then how do you lose angular momentum? This is what our field is working on mainly. There are 20 different types of ideas about what could be the solution. There are various hydrodynamic instabilities. One very popular nowadays, very trendy, is the magnetic winds. Then we have also photoevaporative winds, which can also bring away angular momentum, and then various non-ideal MHD effects as well. So if I understood correctly, during this week, your black hole disks are fully ionized, and you have ideal MHD and alpha viscosity and MRI. So in that sense, we are also different a bit. For us, it turned out that the opacity does change quite a bit around the planet. So this is relatively small mass planet, 5 Earth masses. What you see is the opacity. So it's getting very large, close to the core. And then very in the inner part, it's dropping again because there it reached the temperature where silicate sublimates. And then then the opacity drops. So now this is the vertical direction. There is quite some opacity gradient, and that's going to change the accretion rate and the torques as well. If we go to the giant planet regime, so Q equal 10 to the minus 2, you see the gap region is very low opacity, and we have a very large gradient inside the mini disk or circumplanetary disk, as we call it. So what are the lessons that we learned from planet formation? For us, it's clear now that the thermodynamics matter a lot, and I personally advocate for using radiative simulations. We have found the more heating you have, the less accretion you're going to get, and also the torques are different. The more heating you have, the more likely the object going to migrate outward. Then we have different gap profile if we have radiative simulations versus isothermal. So all in all, everything depends on the opacity, or in other words, the cooling rate. So that's why we need to break away from the isothermal. Then, of course, 3 dimensions matter, and there were a lot of talk about that. So during this week, the same applies for us as well. We have found also that the shocks matter. I will tell you why. We need resolution, in my opinion, in order to get the correct solutions for the accretion and for the torques as well. We should also talk about how do we treat the gravitational softening, whether we use zinc or not. And we have also found that viscosity matters, as well as for us the dust inclusion. So how do we treat the point masses in the planet versus black hole community? So we have also, in both cases, point mass in the corner of 8 south. I personally don't use zinc because what are planets? These are hot gas balls. So they are not like a vacuum cleaner. They cannot accrete everything which is false into their vicinity, as opposite to the black hole case. We, of course, just have Newtonian gravitational potential, and I just learned that you either use the Paczynski-Vita or even GR. Now, this softening or smoothing length of the gravitational potential is in this form, where here we have the smoothing length, which is going to define the planet's surface. So it's very important. I have also seen that this smoothing length shouldn't be too big, otherwise it's going to affect the rotation of the disk, the accretion, and the torques as well. So I believe that the softening length should be as small as possible. If you can resolve the object radius, then that should be the smoothing length. I have seen that there were very nice various gravitational smoothing that you are using in the black hole community, for example, this Gaussian sink. And I think this is also something we should think more in the planet community. So I mentioned before that shocks matter, and here there is an example for that. Plus, it's also showing that the viscosity also matter. So on the left-hand side, here is the circumplanetary disk on the midplane. The middle is the planet. And we have a completely inviscid simulation, so 0 kinematic viscosity. You see that the gas parts are coming in. It's going to encounter the shock front of the planetary wake, therefore losing angular momentum, therefore can get closer to the planet. On the other side, again, it encounters the shock front, losing angular momentum, and this way spiraling downward. However, when you have any kind of viscosity, so the realistic case, you're going to get outward flow in the midplane, the same way as Adam Dempsey showed the other day for AGN disks. So in most of the cases, we're going to have outflow in the mini disk. So these are decorating disks for us as well. So we have also found that radiative treatment or temperature are going to change the torques. So this was our paper back in 2015 in Nature. So if you have heating versus without heating, the total torque looks completely different and changes direction. If you look at here, the more heating we add, the higher we are in this plot. That means we have more and more outward migration. So the more heating means either slowing down inward migration or even reverse direction and going outward. The gaps are also different. So when you use locally isothermal equation of state, then per definition, the gap profile is the same in the midplane as in the upper layers of the disk. Here you see the midplane with the red, and then we are going towards the surface of the disk in this radiative simulation, and you see that the gap profile changes quite a bit, both in terms of width and also how shallow or deep it is. We also see that in the horizontal direction, the gap profile also changes with the heating. So if we have at the planet surface 10,000 Kelvin, then we have a much shallower gap than if we would have just 1,000 Kelvin at the planet surface. So it changes even the gap profile. We have found also that three-dimensionality matters. This is roughly how the material is accreting onto the planet and onto the circumplanetary disk, mainly coming in from the vertical direction, and there is an outflow in the midplane. Then rising up again to maintain this meridional circulation, which we published back in 2014. And the good thing is that by now, this has been observed with ALMA kinematic mapping. Richard Teague and colleagues published a paper in Nature that they found exactly the same circulation for a planet candidate. We also have found just last year that the same goes on with dust as well. So here, this is a vertical slice through the disk. The planet would be somewhere here. The red shows upward motion, the blue shows downward motion, and we're cutting through the spiral wicks of the planet. And you see very well how the dust is lifted up from the midplane and brought up to the surface layers of the protoplanetary disk, as well as it channels in above the gap and deposited onto the planet region. I can show you this better with a movie, a 3D movie. So again, here is the planet. And the gas is coming in, going to encounter with the spiral wick, therefore losing angular momentum, and could spiral down to the planet directly. That part of the gas, which could not be accreted to the planet, going to spiral outward in the midplane and going back by the spiral wick back to the circumstellar disk. So this is a very complex 3D motion, and this is why I believe that we need to have 3D simulations. We not only get a disk solution, so around the planet, sometimes only an envelope forms. And this depends on one hand, the planetary mass. The more massive is your secondary, so the planet, the more likely you get a disk solution. However, we have found that it's not only depending on that, but also what is the opacity, temperature, or cooling time around the planet as well. The hotter things get, the more likely you're going to get an envelope solution. Why does this matter for us? Because if you want to form moons, then you have to have disks. This is the reason why the Jupiter, Saturn, Uranus, and Neptune have satellite systems. They formed circumplanetary disks. However, within the snowline, the terrestrial planets could not form circumplanetary disks. They only formed envelope, and therefore they formed only their first atmosphere, and there was no hope to form any satellites. You can see here how everything depends on the temperature. So here is a 1 Jupiter mass planet, and what I changed here is only the planet temperature, the surface temperature. This is 10,000 K, 8,000, 6,000, and so on, down to 1,000 Kelvin. And you see that you get an envelope solution if things are really hot, and the cooler the simulation gets, the thinner circumplanetary disk you're going to end up with. So we have seen thermodynamics matter, 3D matter, shocks matter, and so on. One of the good things about the radiative hydrodynamic simulations is that you get almost freely observational predictions, since you have the density information, temperature information, both for the dust and gas, and you have self-consistent extinction calculation as well. So we did this in a couple of papers, and we did imaging, for example. In this case, you run the hydro, then we post-processed it with wavelength-dependent radiative transfer software with ray tracing, and then finally you do something being convolution and interferometry depending on the telescope. And this is how it looks like. This is the circumplanetary disk. This is exactly how the colleagues have found the first evidence for circumplanetary disk around an extrasolar planet that is currently forming. This is PDS 70C. It has been shown on, I think, on Wednesday. And here you see the dust that is around the planet, which is inside the circumplanetary disk. We can also do SCDs, circumstellar disk, circumplanetary disk, and how much the circumplanetary disk contributes to the SCD. So I guess the mini disk might also contribute to the SCD of the circumbinary SCDs. And we can also do hydrogen recombination line predictions. We can calculate from the temperatures what is the ionization fraction with the Saha equation. From that, we can do line emissivities and calculate what age alpha flux we're going to assume we can get. And the age alpha is important because it's an accretion tracer line. So the line flux directly proportional to the accretion rate of the object. So in summary, we have seen thermodynamics is a good thing to have. It's going to change the torques and the accretion. You can get observational predictions, but we are in very different opacity and temperature regime for the planets versus the black hole case. We also agree that three-dimensionality matters. For us, dust inclusion matters, and I don't know whether this could be important maybe in the outer part of the AGN disks. We need high resolution to resolve the object surface so that we can have more correct solutions. And we should, I think, agree how do we treat things and gravitational smoothing. So when we compare our results, we really compare apples to apples. And what I learned this week, that we should really read each other's papers, because I feel like we are reinventing the wheel sometimes. And so I think we can learn a lot from each other. Thank you for your attention.
Thanks, Judith. Completely agree. So, Julian?
Could you expand some on how exactly you do the radiation transfer?
So flux limited diffusion approximation with the two temperature approach. So this is equivalent of the Commerson 2011 paper. And you use a Rosaland mean opacity, a Planck mean opacity, and you use an opacity table that is appropriate for your science goal. And based on what is the temperature and the density in a cell, you look up in this lookup table and get the opacities.
Thanks.
Yeah, so this is fantastic. You're mentioning how important opacity is, and also that you have 1, 2, and maybe even 3 fluids. So what's the key takeaway when you allow the dust to decouple from the gas in terms of the evolution of the disk and the impact it has on the accretion of your protoplanet?
Yeah, so given that for us, dust is the main opacity source, therefore, if you have dust, then you have much higher opacities. That means you're going to get a more optically solution, which usually means higher temperatures, which again means a reduced accretion and reduced torques, So the torque going towards the outward migration regime in this case. Two fluid, yeah.
I'm curious about what happens to the spin of the planet where you get that sort of polar inflow and excretion disk kicking out, because it'll be really interesting to see what happens to black holes and AGN disks.
Yeah, that's a
that
very
context.
good question. In the planet field, we haven't put in spin. Nobody have. I think we did not really. Well, I mean, it's not so easy to put that in, but I just learned from the black hole case that matters. So that's definitely something we should do in the future in the planet community. And I think it's going to change things, as you have found.
Great. Jeff, go ahead online.
I actually had the same question. I've always sort of been curious as to why gas giants aren't spinning at breakup, and if they're accreting sort of low increment of material from the poles, that could explain that. But excellent talk. Thank you. It would be interesting to see what the conclusions are for spins of planets.
Yeah, thanks.
Here you go, Andre.
Thanks. Ondřej Pejcha. I have a question about dust from the point of view of common envelope where things are happening fast. So you assume that the dust is just there, but could you estimate how fast the dust forms from the gas?
So we cannot do coagulation inside the hydro, because for that you would have to solve like 100 different partial differential equations to get all the sizes right, and you have to have at least 10 different sizes. So that's just not available for us with the current computers that we have in 3D. However, there was one work in 2D by Hui Li and the Los Alamos people in 2D, and it seemed that matters a lot. If you include coagulation, that going to change, for example, the profile of the gap and a couple other things as well. I don't know. I'm not a dust coagulation person.
Zoltan?
I hear you.
The details of how, so this, I think it does the meridional circulation exist even without radiation?
Yes. Yeah. First we found in the isothermal simulations, then we also find in the radiative, and now it has been observed. So
is the torque changing sign because the something wrong with no, it's not wrong.
The torque changes signs.
So the torque changes sign because the radiation does change the details of this
yes.
meridional circulation. So can you say more on this?
So the inclusion of radiative transfer doesn't going to change the dynamics, the flow directions. However, the inclusion of radiative transfer means that the accretion rate is going to be much smaller because of radiative feedback that you know all very well. Then if you have radiation transport, then the torques are getting more into the outward migration regime. So it just changes the torque depending on where you are in the protoplanetary disk. It can be either inward migration or outward migration. What we do in our field is we are making migration maps. So we map the entire protoplanetary disk and we check what is the torque direction, and this way we will know whether the planet would move inward or outward. So this is, I think, a good recommendation which maybe you can do for orbital evolution.
Okay, yeah, question, yeah, thank you. I want to just get clarified about this sync treatment. Like, I guess what you are saying is that in your simulation, you have such a high resolution, you can actually resolve the physical size of the protoplanet.
Yes.
And then you are also confident you take into account, you were able to put in all the microphysics of the cooling in there, around that region. Therefore, it's more appropriate to not use the sink.
Yes.
Right, and the post black hole in the black hole case, no hope to resolve in the region, right? So that's what you're saying, right?
Yeah.
So I guess the question is just if you could, if you do this, how does the m dot accretion rate onto the planet compare to, for example, naive expectation of boundary equation, for example, right? If you given a background of given
So,
a thick background for the background for the kind of disk, right?
yeah.
How
Yeah,
does
so
it compare?
in this case, because you don't have sync, you're going to have an envelope which is getting more massive and also having a larger and larger radius. So this is what you need to account for when you measure the mass accretion rate onto these protoplanets without sync. How does that compare with Bondi accretion? Where in the Bondi accretion formula, there was already written that the accretion rate is inversely proportional with the temperature because it's CS in the denominator, which is directly proportional to the temperature. So the higher the temperature gets, the lower accretion rate you're going to have. So we have also this dependence. However, the Bondi accretion formula did not seem to work very well for me. I don't know, Matthew, did it work for you very well? Did it give back the exact solution?
I haven't done this for like 12 years, but yeah, we didn't compare to Bondi accretion, but we compared our accretion rates. This is work done by Ben Aliff back in 2010 or so to like the one-dimensional planet formation calculations. And from memory, we got very similar accretion rates given the same opacities. I mean, the rate at which these planets can accept gas from the nebula is all determined by how quickly they can cool, as Judith was saying. So it really depends entirely upon the opacity that you use.
Yeah.
And that's been known right back to like Pollack, 1996 and so on, maybe even earlier.
So the accretion rate is directly proportional to the cooling time. You can have an equation for this. So the more cooling you have, the faster the planet going to accrete.
Yeah, so I was just, your comment about making migration maps of the disk based on conditions is very interesting. And one of the things but connecting actually the conversation that was just going on, right? So if you have a different, for the black hole case, right, the mass of your black hole will, scale your accretion capacity, right? And so then different mass black holes might have different accretion luminosities, which then might respond differently to if you have some fixed opacity, some gradient might get out and some might not. So you might see like a different torque for a different mass object. I'm just wondering if that's anything that you all have to think about.
Yeah. I mean, we run these migration maps for various planetary masses. And so the migration map, one axis is the mass of the planet, the other axis is the radii inside the disk. And you can, but we don't have, or I personally don't add extra accretion luminosity. The reason being because you already have the accretion inside, because as the gas is falling onto the planet potential, there is adiabatic compression, which heats up the gas. And I believe that traces very well the gas accretion luminosity. You don't have to put in an extra one. So I don't know in the black hole case, if you have to put in something, then of course you already have an influence on what comes out in the migration map. I see that.
Thanks.
Okay, thanks again, Judith.
Thank you.